Last video for today's set of notes is going to go on and talk about isothermal processes and adiabatic processes. And I apologize if I'm getting less and less coherent Friday afternoon making these videos. You're going to get a rambling Chorman. Alrighty? So, let's take a look at isothermal processes here. Okay, let me get my notes straight. So, the first thing that you need to know for isothermal processes is that the temperature doesn't change. And the way that we do this is we place our piston cylinder assembly in a heat bath, all right, that's going to maintain a constant temperature of the gas by supplying and removing thermal energy. So the gas laws, when we look at this with the gas laws, all right, the unified gas law, we know the temperatures are equal. So we end up with the relationship that we know from Boyle's law, okay, and that's if the pressure increases, the volume is going to decrease, okay. So we're going to talk about this expansion and compression stuff in the next slide. Again, using the first law of thermodynamics there, all right, we see that delta U is directly proportional to delta T, so it's isothermal, there's no change in temperature, there's no change in internal energy, and our resulting relationship is this one right here, where the change in thermal energy is directly equal to the work done by the gas. All right, so let's take a look at what this stuff means. All right, so for the expansion, okay, since we are going to be increasing our volume, the gas must be doing work on the cylinder, the piston, on the piston. So we see that thermal energy must be flowing in at the same rate that the gas will be doing the work. And then for compression, again, we need thermal energy to flow out at the exact same rate that the work is done on the gas, so that energy is leaving the system in that way. Again, we want to make sure that the temperature stays the same, so that's why we're saying it's at the same rate here. Okay, no changes in internal energy is what our goal is. Okay, if we have the PV diagram here, all right, what we see, since temperatures are constant, is that P is related to V, and remember P and V are related inversely, so we end up with this hyperbola, and this curve, an isotherm, okay, is going to be this hyperbola on a PV diagram, all right? And so what it shows us is that all states on one isotherm, right, have the same internal energy. In other words, they have the same temperature, okay? That is all the different possible combinations of the pressure and volume at that temperature for that amount of gas. The further the isotherm is from the origin, the higher the temperature, the higher the internal energy, all right? And the change in internal energy between two of these lines, okay, is path independent. Remember that change in internal energy doesn't matter as long as we have the same delta T, okay? Going between the two of them doesn't matter which pressures and volumes we occupy along the way. So if we're expanding, okay, the volume is decreasing, moving to the right, the work is positive. Just like we had before, when we had those little cases, we see that this area underneath the curve, going left to right in calculus, we end up with this positive value for our work, and therefore the thermal energy added is going to be positive. And if we're having a compression, again, we see that the work done is negative. Do that little integral right here, okay? And if the work done is negative, going from right to left, the thermal energy added must also be negative, okay? So these are the big ideas for an isothermal process. Again, the main things that I want you to get out of these processes, okay, are what the lines look like, on a PV diagram, okay, and what happens to the first law equation, right? I want you to, be thinking about that, and that's why we started this whole thing, this whole section talking about, on thermodynamics, talking about the internal energy being directly related to temperature. There's some really important things happening here, okay, with that. So being able to connect those is what's really important, okay, as well as knowing which variable is remaining constant. All right. So the last one, process that we're going to cover in this section is an adiabatic process, okay? And an adiabatic process is one where we have a perfectly insulated system, okay? And thermal energy cannot enter or leave. So that means delta Q is now 0 when we look at the first law, okay? So if delta Q is equal to 0, what we have is that the change in internal energy is equal to the work done by the gas. So if we have an ideal gas, okay, we know that the internal energy is directly proportional to the temperature. So any change in temperature, all right, now based on an adiabatic process is going to be directly proportional to the work done by the gas, okay? So we look here.
Tonight, if you're in the building.
Sorry about that intrusion there. I was able to pause it just in time, okay? So let's consider an adiabatic expansion, all right? What is happening there? So if the gas is expanding, it's going to be doing work. As it expands, the volume is going to increase. As it increases, though, the work done by the gas, okay, we have this loss of internal energy, okay, because the negative work done by the system is going to be equal to the internal energy, all right? And if we lose internal energy, that means that we have a negative change in temperature, okay? That's getting that whole idea that the negative work done by the system is directly proportional to the temperature. So with positive work, we have a negative change in temperature, and if the temperature, since we're losing thermal energy as well here, okay, as we have this expansion, there are fewer collisions at a lower speed happening, so therefore the pressure is also going to decrease, okay? So when we look at the curve here, we're actually dropping in temperature, so we're going between two different isotherms, okay, when we have our process drawn on a PV diagram. And so what we see is that our adiabatic curve is a little bit steeper because it has to go between isotherms, you know, based on the fact that negative work is directly proportional to the change in temperature, okay? So that's what that curve drawn right here is, this little guy, okay? So that's our adiabatic curve going between two isotherms. So for a compressing the gas, work done is on the gas, it's going to heat it up, okay? So the first thing we know is the volume is going to go down. The internal energy, all right, is going to increase as we're adding energy to the system, okay? So really it's work being done on the gas, it's in that negative work, all right, in that sense. And so because our volume is decreased, we increase the energy, all right, the pressure will go up as the average speed of the molecules will increase, and the frequency of the collisions will also increase with the walls of the piston and cylinder, all right? So in that case, okay, we're going from a lower temperature to a higher temperature, and it's going to be a drop in pressure, volume is going to be an increase in pressure, and that's what that is going to look like. So that is our adiabat, all right, for a compression, okay? So let's look at some examples here, all right? Starting always with our almighty first law of thermodynamics, all praise the first law. Amen. Okay, so 410 joules of heat energy are added to an ideal gas, causing it to expand at constant temperature. What is the change in internal energy of the gas? Well, since it's constant temperature, delta U is equal to 0. All right, so we know here, all right, that we have an isothermal, all right, heat addition. So how much work is done by the gas? Actually, it's going to be an isothermal expansion is what we have, okay? So since the delta Q must be equal to the work, we have 410 joules worth of work being done. And then the question is, how much work is done on the gas? Well, since we've reversed our phrasing, it's negative 410 joules, okay? Since the gas is doing the work. And it's just telling us the direction of the way we were saying that is opposite. If an ideal gas is allowed to expand adiabatically, the internal energy of the gas changes by 2,500 degrees. The question then is, does the internal energy of the gas increase or decrease? Okay. Well, with the expansion, we had said before, okay, that the temperature must be decreasing since work is directly proportional to, negative work is directly proportional to the change in temperature. So expansion tells us it's positive work, so we must have a negative delta T. With negative delta T, we have a decrease in temperature, dropping to that lower isotherm. Go to the graphs on the previous page for that, right? So to determine the thermal energy added or removed from the gas here, all right, we need to be thinking about, let's see here, the type of process that this is, and we're told it's adiabatic. So since it's adiabatic, that means that there's no thermal energy being added or removed, so delta Q is equal to 0. So the work is equal to the change in internal energy, all right, and that's going to be a positive 2,500 joules, okay? So that is that example right there. That is an adiabatic process. The next set of notes, we'll go over thermodynamic cycles and the second law of thermodynamics, and we'll be doing practice next week, getting ready for the test in 2 weeks, and I hope you have a good weekend.